Welcome everyone to my lecture where I'm going to tell you a bit about how we are trying to understand the atmosphere a bit better on a molecular level. I also start off first with a bit of personal background. So I grew up in Austria, got my undergraduate degree in physics from the University of Vienna. After that I moved to Helsinki to get my PhD from the University of Helsinki, working mostly on atmospheric aerosol particle formation experiments, and I spent a lot of time also at CERN where we did experiments in a big atmospheric simulation chamber. After I got my PhD, I went to the US to do a postdoc for 2 years at the University of Washington, and there I mainly learned various fancy ways of how to use atmospheric mass spectrometers. And since 2017, I'm a member of the faculty at the University of Eastern Finland. And my research here mainly concerns surface air and air aerosol interactions. And the common theme in my research activities it involves chemical ionization mass spectrometers, or CIMS. But why are aerosol particles important in the first place? For one, they have a cooling effect on the climate. They can directly reflect sunlight back into space that would otherwise be absorbed by the Earth's surface. And the aerosol particles also act as the seeds that are required for water vapor in the atmosphere to condense into cloud droplets. So if we have more aerosol particles around, we end up with more clouds that are longer lived and also brighter. So again, more solar radiation is reflected back into space. But aerosol also have a negative impact on life quality. They can lead to drastic reductions in visibility, and they are also linked to increased mortality because they are generally toxic. And it's estimated that aerosol pollution leads to millions of premature deaths per year on a global scale. So where do those aerosol particles come from? For one, there is direct emissions, and we call those particles primary aerosol. And there is both natural and anthropogenic sources for this primary aerosol. Some examples are shown here. Natural sources are usually related to wind, wave, fire, or biological activities. And anthropogenic sources are usually related to humans burning something. But much more interesting, in my opinion, and arguably more important, are so-called secondary aerosol particles. And those are particles that are formed in situ in the atmosphere by the conversion of trace gases into liquid or solid aerosol particles. And again, we have both natural and anthropogenic sources of relevant trace gases. Examples shown here are photochemical smog in Houston, Texas, which is at least to a big part due to also anthropogenic trace gas emissions. And pretty examples of natural secondary aerosol is the blue haze that one can often observe over forested hills, shown on the right. So which are these aerosol-forming trace gases? The vast majority of those trace gases are, very generally speaking, molecules that contain oxygenated forms of carbon, sulfur, or nitrogen. And out of these, the carbon-containing compounds are the most important probably, and definitely the most complex class of compounds. And that's because carbon atoms are very good in making molecules. There is myriads of molecules that are arranged by basically networks of carbon atoms that we call organic compounds. And these oxygenated organic compounds, there is at least tens of thousands of different species of those in the atmosphere, so it's a very complex class of compounds. And they are also formed in situ in the atmosphere typically by the atmospheric oxidation of so-called volatile organic compounds, or VOCs. And those VOCs are directly emitted typically from surface processes. And sources of those VOCs are, a lot of the sources are biogenic. They are emitted from vegetation, mainly trees, other plants. And anthropogenic sources are traffic, industry, cooking activities, and also volatile consumer products. And it's worth it to note also that these VOCs are very often compounds that we can smell if they are in a sufficient quantity. For example, the nice smell in forests is due to the VOCs that are emitted by trees there. And for a specific example, let's pick one such tree here as the emission source. And the typical VOC that would be emitted by the tree would be this guy that we call alpha-pinene. It's a molecule containing 10 carbon atoms that are arranged in 2 interlinked rings. It's already a fairly complex molecule. And it's also fairly reactive. For example, reacts with ozone in the atmosphere and forms hundreds of product compounds. And I chose one to show here, pinic acid, which has now gained 4 oxygen atoms compared to the parent compound. And the key molecular property that has changed now through this process is that the molecule has experienced a significant reduction in volatility. So volatility is essentially the tendency for a molecule to want to be in the gas phase. So alpha-pinene has fairly high volatility, pinic acid has low volatility. And this low volatility now enables pinic acid and similar compounds to condense into aerosol particles and participate in the formation of particles. Okay, so far for the background. How do I try to measure compounds like this? So my tool of choice is online chemical ionization mass spectrometry. And at the core of this instrumentation is usually an ion molecule reactor of some sort, which is a region where we mix sample molecules together with reagent ions. And these reagent ions are chosen such that they softly ionize the sample molecules, the sample trace gases that we're interested in. An example shown here is iodide reagent ions that usually form ion clusters with many trace gas molecules that are interesting from an atmospheric chemistry point of view. Some examples shown here. And now that these molecules are ionized, we can manipulate them with electric fields, and we can transfer them into mass analyzers, which usually requires a high vacuum. And an example mass analyzer is shown here, which separates ions based on their time of flight, exploiting the fact that heavier ions will fly more slowly after being accelerated by the same electric field as lighter ions. And then we can measure the exact mass of those ions, and from the exact mass we obtain their composition. And another key feature of the instruments we like to use is that they're fairly compact, and we call that also field deployable, because we can deploy them into the field. And the first example of my research that I'm showing is one such field deployment of a SIMS instrument. You can see that instrument here in this white box. It's deployed to the Sikaneva wetland, which is close to Orivesi in southern Finland. And there was a campaign during spring and early summer a couple of years ago. Behind that box, you can also see some fancy inlet system that allows us to measure these trace gas concentrations with very high precision, and also capture very fast fluctuations. And on top of the inlet is a sonic anemometer, which at the same time measures the 3D wind vector at very high frequency to measure the turbulent eddies that occur at that sampling height. And by correlating these fluctuations of the trace gas concentrations with the fluctuations in the wind, we can then calculate the emission flux of compounds from the surface. That's a technique called eddy covariance. And for this deployment, we chose an ionization scheme that is sensitive to the most important biogenic VOCs. They are listed here in order of increasing complexity and size, starting with isoprene on the left and then various terpenes. And it's worth it to note that those compounds tend to become increasingly more difficult to measure the larger they become. And this deployment, with this deployment, we were able for the first time to get direct diterpene fluxes even from a wetland. But in terms of emission abundance, it was actually isoprene that we found was emitted the most. So I continue with that. And the key finding of that study was that these VOC emissions were much more strongly dependent on temperature than emission models had been assuming till then. especially when temperatures went above about 20 degrees, emissions really kicked off, and we also observed the heat stress effect where emissions remained elevated after a very hot period, even for at least a week, and those are the red dots in this plot. And together with collaborators at UC Irvine in the United States, we figured out that it's most likely sedges that are responsible for this strong temperature dependence, this high temperature sensitivity. Sedges are a class of grass that also likes to grow in boreal and Arctic grasslands and wetlands. And in that study, we also plugged in an updated parameterization into a global emissions model to see how much we have been underestimating isoprene emissions from boreal ecosystems. And the result, one result is shown here, interestingly showing that the most significant underestimations occurred in areas where we basically don't have any measurements at all, like remote Siberia and northern Canada. Okay, and then I wanted to quickly show you one way that we also use SIMS techniques to also measure the composition not only of gases but also of aerosol particles. And an example is the Figaro inlet. It's a filter inlet for gases and aerosols, and an advantage of that inlet specifically is that it also allows us to measure the volatility of the aerosol constituents besides their composition. And in principle, at least, this technique is very simple. We collect aerosol particles first on a Teflon filter, seen in white in the schematic on the right side. And on the left side, you also see an electron microscopy image of that filter that includes also aerosol particles that had been collected on the filter, some of them circled in red. And once we have enough material collected on the filter, we move over the filter to just in front of the SIMS. And for that purpose, the whole inlet is actually mounted, plugged on basically just in front of the SIMS instrument. And now we have it in front of the instrument, and we flow nitrogen through the filter and gradually heat the nitrogen. And through this gradual heating, we thermally desorb the molecules from the collected particles, and then suck these desorbing molecules also straight into the SIMS for analysis. And by gradually heating, we also managed to make the higher volatility compounds desorb first at lower temperatures and the lower volatility compounds only later. So we can also get the handle on the volatility of the aerosol constituents. And an example results are shown here. This is for a test aerosol we made by using a series of polyethylene glycol polymers. These are quite handy because you can buy them in different lengths. So you get, and then we managed to get them all into the same aerosol particles and get them onto the filter. And indeed, the gradual thermal desorption separates these polymers also by volatility. You can see here that like the PEG of order 6 desorbs already before 40 degrees centigrade. With a chain length of 15, you need much more than 100 degrees. And these temperature range actually corresponds to more than 10 orders of magnitude in terms of volatility. And the key feature here is that we are also able to explicitly model this desorption process with a model we developed, and then use these model simulations and fit them to the observations. And this figure actually also shows the model fit to the observations, and through that we can get quantitative information on volatility. And finally, I wanted to spend a few words on research and development needs that I find are related to the research I've shown. This is really a very small selection, but one issue we have, for example, is that emission models are still very simplified often due to a lack of observations. For example, a commonly used emissions model is using grassland as a certain ecosystem type, and it's treating emissions from grasslands all the same, irrespective if it's a savanna in Africa or an Arctic tundra, right? So I believe we need still more studies of underexplored environments and scenarios to better get a more realistic handle on emissions. And also, I mentioned a couple of times the monoterpene alpha-pinene, but monoterpenes are really a complex group of compounds. This is only a small selection of isomers of monoterpenes shown here. Many measurement techniques and also model parameterizations treat them all the same, but they are really very different in terms of chemistry they can do, and therefore in their aerosol formation potential and things like that. And in terms of organic aerosol composition and volatility measurements, we are currently making progress within this Wilma Center of Excellence that I'm a PI in since 2022. And for example, we are trying to make these thermal desorption techniques more sensitive so that we are able to study smaller aerosol particles, especially below 20 nanometers. These are really difficult to measure, and also to capture faster time scales, because some of important chemistry happens actually quite fast. And then we are also dealing with large data sets and measurement uncertainties that we are trying to tackle with machine learning tools, for example. And that brings me to my thank you slide. Thanks to my team members and collaborators to make such work actually possible, and the public for their money and for your attention.